All right, Mr. Arnold here, looking at 18.3, taking a look at nomenclature and a little bit more about bonding and how these all kind of work for both ionic and covalent bonding. So we're going to start with ionic bonding. You know it's ionic bonding for a couple of reasons. Number one, you have a metal, and so anytime we have a metal and a non-metal bonding together, you know you have ionic bonding. So magnesium is our metal, and our non-metal is going to be sulfur. And that's where we're going to begin. I apologize for that. I'm back here. So we got magnesium, the metal. We got sulfur, the non-metal. So that makes this one an ionic bond. Just kind of reminding us of what's going on. Why is it ionic? Because as you recall, magnesium is in family 2. It has 2 valence electrons that it's going to try to get rid of. So if it is trying to get rid of electrons, it's going to be a positive 2 charge. This positive 2 charge is what we also call the oxidation charge, or the charge number. Oops, oxidation charge. So when we take a look at our elements that we are using, the charge, the number of electrons they give up or take on, is also known as the oxidation charge. Sulfur is in family 16, so it has 6 valence electrons. It has a -2 oxidation number, and that's because it likes to take on 2 electrons. Let me pause right. Alright, so we know that magnesium wants to get rid of 2 electrons, so it's going to donate its electrons over to sulfur. Sulfur wants to take on 2 electrons, so it takes 1 magnesium atom to satisfy or to take care of 1 sulfur atom. And we know that's true because they have a +2 charge over here for magnesium. We have a -2 oxidation charge over here for sulfur. 2 plus -2 is 0, which means that this is now neutral and a balanced ionic compound. With that being said, being the balanced ionic compound, now we have to name it. When we name compounds, the positive number, the element, which is always the metal, is going to come first. So that is going to be magnesium. The negative oxidation charge, or the non-metal, is always going to come second. And we are going to start to write the name out, but then we are going to take off the last few letters and add the IDE ending. This compound right here is magnesium sulfide, because 2 electrons from magnesium go over to the 2, or fill the 2 that sulfur needs, and the MgS is now called magnesium sulfide. So let's take a look at a little bit different one here coming up. This one's a little more complicated because, again, we have aluminum. Aluminum is in family 13. Family 13 has a +3 charge because it has 3 valence electrons. And we have oxygen, who is in family 16, and it has a +2 charge, because, or I'm sorry, -2, because it likes to take on 2 electrons from there. Again, these are the oxidation numbers. The oxidation numbers just tell us the number of electrons that are either gained or lost. So for aluminum, we're going to donate to this electron, or these electrons, over to the oxygen. This oxygen is now satisfied. It is good to go, but the problem is we still have this guy over here that needs to go somewhere else. And as we learned in the last unit, we're going to add more atoms of the elements that we already have. So we're going to add on another oxygen because we got to get rid of the 1 from aluminum. So this one comes down here. This aluminum atom is now satisfied, but we haven't satisfied this oxygen. So again, we're going to keep going back and forth until we can get all of these electrons taken care of. This oxygen only needs 1 more. So this oxygen now has all of its atoms. It is satisfied, but this aluminum is not satisfied. We're going to add, oops, wrong color there, sorry. We're going to add in 1 more oxygen. And this electron is going to come down here. This electron is going to come down here. Now each one of those has 8 around it. So this oxygen is good. We've gotten rid of all of our aluminum electrons. This aluminum atom is good as well. So if you take a look at this, the chemical formula is going to be Al, because the positive always comes first, and there's a total of 2 aluminums, so Al2, and then we're going to put O because the negative ion always comes second, or the nonmetal, and there is 1, 2, 3. What this is telling us is we need 3 oxygen atoms to satisfy the need of 2 aluminum atoms. If we are going to write this formula, again, the positive always comes first. Aluminum is always going to come first, and we never change that name. And then the second one is going to be the nonmetal, or the negative one, and we drop the ending, and we add the IDE ending to it. So this is aluminum oxide. Now, one of the biggest problems we have with this is how do you actually know what to use, and how do you know that you need 2 or 3? You can draw all of this stuff out, which is fine, and that's what I did. It's the way I like to do it because it's visual, but you can also do something else. We know aluminum likes to give up 3 electrons. So if it likes to give up 3 electrons, and we know oxygen likes to take on 2 electrons, we kind of start thinking in the idea of the least common, multiple. What number does 3 and 2 have that is least common in each other, which is 6? So how can I get this 2 up to a 6? I multiply by 3. How can I get this 3 up to a 6? I multiply by 2. So that's why it's Al2O3. I need 3 -2 charges to get to 6, and I need 2 +3 charges to get to 6. Again, using that kind of least common multiple thinking or process there. There are exceptions to every rule, and like always, our transition metals, as we had talked about, are the exceptions to the rules. We will not mess with transition metals, but sometimes iron likes to give up 2, sometimes iron likes to give up 3 electrons, and in this case, we know, and I'm going to use X's, they're a lot easier to write on this board than anything else. So we know chlorine likes to take on 1. Well, where are we going to get that? This one is going to come here. What do we need to do? We need to add, that's right, another chlorine atom. Why are we adding another chlorine atom? Because we need to get all of these electrons off of the iron. So we have 1 more. We're going to add a final chlorine atom here. This one's going to come here. So what is this one going to be named? Well, by taking a look at the picture, the name for this one is going to be, again, the positive one first is going to be iron. And then the negative one is second. It's going to be chlorine. But how many chlorine atoms do we need? We have 3. So iron chloride is going to be the name for this substance. Again, the first one always remains the same. We don't change the metal. The second one, the nonmetal, is the one that we drop the ending and add IDE. However, since this is a transition metal, and because it can give up multiple different electrons, we have to add in a Roman numeral to tell us which iron we are actually talking about. So this is really called iron 3 chloride, and it tells you that it gave up 3 electrons. It's FeCl3. If this was iron 2 chloride, it would be FeCl2, and again, it would be written the same way, with the exception of you would have 2 in the parentheses, and then chloride would still be chloride on the end. Alright, so that's what we got for ionic bonding. Remember, ionic bonding is always with a positive metal, which always comes first. We never change the name. We have a negative non-metal that always comes second. We always change that name to an IDE ending. For the transition metals, we have these Roman numerals that get plugged in between to tell you exactly how many electrons have been given up or taken on. Another exception to the rule are these things called polyatomic ions. Although you don't need to memorize these or really fully understand these, what you really need to know is that these are a group of ions that actually behave or act as if they are one single one. So we have nitrogen with 4 hydrogens. They are going to behave as one big solid group. This group is called ammonium. So they have their own name. So ammonium actually behaves as if it belonged to the first family, which means it has 1 valence electron. and it has a +1 oxidation charge. This group over here, NO3, are our nitrates. And this group here actually acts like it belongs to family 17, which means it has 7 valence electrons, and it's only looking to pick up one more, so it has a -1 oxidation number. So when this guy donates its electron, you now have the substance NH4NO3. You have 2 polyatomics that are working together, combined together to form ammonium nitrate. When you see the ATE ending or an ITE ending, that is telling you that you are working with polyatomic ions. Most of them have an ATE ending, a few of them will have an ITE ending, and a couple of them will have the IDE ending. But just kind of remember and focus on ATE. We're talking about polyatomics, which are groups of atoms that are working and behaving as if they are one single atom. And when they combine together, again, the naming rules are the same. The first name is never changed. The last name, you drop the ending and add the AT ending for polyatomic ions. All right, a little bit on covalent bonding now and talking to how we actually name these covalent ones. Again, there are different sets of rules. These electrons are now being shared. They're not being given up or taken on. And the attraction force between the shared pair of electrons is what is actually going to keep them held together. So we have hydrogen. Again, hydrogen has 1 valence electron. We have oxygen. Oxygen has 6 valence electrons. So hydrogen and oxygen are going to share this pair. They both get to use it. Hydrogen has 2. It's good. Oxygen, 1, 2, 3, 4, 5, 6, 7. We're still missing 1. So what do we do when we're missing something? We can just add that something to the other side. Again, we're going to add the same element that we're talking about. We're still adding hydrogen. So hydrogen is going to share an electron with oxygen on this side. Again, hydrogen has its 2. It's good. Oxygen now has 1, 2, 3, 4, 5, 6, 7, 8. It's now good. So this substance is simply known as H2O. You guys call this water, which you are technically correct. However, the actual covalent name for this compound is dihydrogen. The first name does not get changed. It's still the same kind of ionic rules here. We're leaving the first name the same. The second name is going to have an IDE ending on it, but this is going to be called monoxide. And it's mono because we only have 1 atom of oxygen, and it's oxide to show that it is actually bonded together. This one is dihydrogen because we actually have 2 atoms of hydrogen in this mix. If we wanted something else, we've talked about this one before, H2O2, which is hydrogen peroxide. Its technical name is dihydrogen. Again, we're not changing the name itself for this one, just adding the prefix. And then this would be dihydrogen dioxide. And the di for this representing the 2 atoms of each hydrogen and oxygen that we would need. Again, this is covalent bonding. Covalent bonding is a little bit easier in terms of naming because we're looking at the prefixes or the subscripts to give us the prefix of what we need to add. It tells you exactly how many atoms of each you need. Where ionic, it tells you a little bit more. You have to figure it out by drawing out the diagrams to see how that looks. A couple of common ones that you need to be familiar with. We're just going to kind of write them out real quick, just so that you know. 1, the prefix for anything on 1 is going to be mono. Di for 2, tri for 3, tetra is 4, penta is 5, 6, 7, we'll go 8, and then we'll skip 9 and go to 10. These are the kind of the most common that you're going to have. Hexa, hepta, and that's supposed to be a P, and then octa, and then the last one is simply deca. Those are the prefixes that you need to be somewhat familiar with. just so that you can tell how many atoms that we are actually requiring you to have in there. So if you had something like H4Cl7, this would then be tetrahydride, and then it would be tetrahydrogen. Don't change the first name, heptachloride. And again, if you know the name, it tells you exactly what the formula should be. If you know the formula, you should be able to write out what the name actually is. And that's, again, for covalent bonding. The last thing about covalent bonding, and I did not mean to do that. Sorry. The last thing about covalent bonding is the first letter, if it is by itself. So if we had CO2, which is carbon dioxide, we do not add a prefix. We would not say this is monocarbon dioxide. It is just carbon dioxide. The only time we add a prefix to the first one is if there are 2 or more atoms involved. The second one always gets a prefix. Whether it's mono, whether it's deca, whatever it happens to be. So the first one, only if it's 2 or more. The second one always gets the prefix that's involved in there. Hopefully this helps. As always, I tell you, if you got a question, please come up and talk to me.